Okay, we'll move ahead with our second talk of the session. Adam Pease will speak on embedding SUMO into set theory.
Okay, so thanks very much for the introduction. So this is work really driven by Chad Brown. He's doing all the core formalization. And this talk is about embedding the suggested merged ontology into higher order set theory. Josef is helping us communicate with each other, since there's a lot of really heavy higher order math that I'm not terribly familiar with, but I am the expert on SUMO, so I can bring that to the table. So what is SUMO, for those of you who aren't already familiar with it? It's a project I've been working on for about 20 years. It's completely open source. It has about 20,000 concepts and 80,000 statements about those concepts that attempt to define them, mostly in first order logic, but with a significant amount of higher order statements. So it is an attempt to say what's true about our common sense world so that we can do some common sense reasoning. And one of the challenges that we've had is knowing whether SUMO is logically consistent. Theorem provers keep getting better. We keep finding problems and fixing them as we go along, but we want to do better at that. So I can say, is it consistent? Well, most of the time, as far as we know, at least for the first order logic concept. We've gotten better in first order, had a big jump improvement thanks to work that Stefan did in E, generating essentially automatically smaller problems than trying to just prove faults on all of SUMO. He can automatically generate smaller connected sort of subgraphs of terms and their definitions that we then have a lot of good luck at finding fairly deep problems in SUMO on. We've got a small number of hand-generated test problems that have been part of the TPTP suite and used on task. We do testing with Vampire and E at times, trying to just prove faults and letting it run for days. That works well. We've also got some simple deterministic, guaranteed determinate, algorithmic implemented special purpose checks to find things like type conflict problems. I should also point out that we can, even when there is an undetected contradiction in this very large theory, we can still do useful things because we have essentially islands of consistency relevant to the particular query we're asking. So we can get reasonable proofs, good answers to problems we pose, even when there may be a very deep contradiction somewhere else in the theory. So it's not a complete killer to have a contradiction on a large theory, because contradictions are completely clear to us when we find them during the course of theorem proving, because there are cases where we don't actually use the conjecture. We have this very clear flag that, oh, there is a problem here. However, again, we only have a few experiments that we've done in higher order logic. We don't really know whether our higher order logic content is good. For those of you who are interested, everything is online at ontologyportal.org, and all of the tool set that we have is also online at GitHub. So we had an initial formalization of SUMO in THF, thanks to work that Christoph Benzmueller did together with me from about 2008 to 2010. It's, in retrospect, really just mostly a syntactic translation to THF. It did fix the interpretation of a few things in SUMO, such as relations that have a variable arity, a variable number of parameters, and then the associated fact of row variables, variables that can stand for multiple arguments at one time. We didn't use type guards at that time. SUMO is essentially a sorted logic. Every relation has a type signature. And so for our first order translation into TPTP FOF and TPTP TF0, we make heavy use of these type guards to prevent unintentional conflicts. If we don't use type guards, we get contradictions that are just spurious because we're allowing the system, any sort of proof system, to try to find bindings for variables that actually don't make sense, that violate our type restrictions. One key thing that we haven't done, that we still haven't even done in the current work very much of, is trying to implement possible worlds or Kripke semantics to really give modal operators some semantics. So let me be a little more concrete about what we have in SUMO. So we have a host of 2-3 dozen higher order relations. We have things like epistemic operators like believes or knows, deontic operators like has purpose, temporal operators like holds during are used pretty frequently. So some formula holds true during a specific time period. That's really hard to say a lot of things about the common sense world and not temporally qualified. So this one gets used very often. And let me give some concrete examples of rules. Forgive me, I hope some of the SUMO syntax will be immediately obvious. It's pretty friendly. So this just says that during a time, if a particular text had the modal attribute of being a law, there must have been some earlier time, and this is a bit specific to the American legal system, that there was a legislative bill that was the modal attribute of that same text, right? So things have to become a bill before they become a law. Or if there is a criminal action, it necessarily means that there is some law that contains a certain body of information. The realization of a particular action was this crime, and those two things weren't consistent. So what happened wasn't consistent with the law, it was a violation of the law. That's the definition of a criminal action. All right, so why do higher order set theory? Why not try to tweak Christoph Benzmüller's original translation, which is sort of a parallel possible effort? This is early work. We don't know how exactly it's going to work out. But there is this nice correspondence, natural correspondence between the way that SUMO does certain things and looking at the world as sets. So we have simple things like an instance. So what Adam is an instance of the class human. And you can treat that as Adam is a member of the class human. All right, very, really obvious stuff. Same thing with subclass, right? So human is the subclass, is the subset of the class primate. And then we get to the slightly more interesting stuff. We have an operator called kappa fun, which calls out a variable in a formula and gives it a set of conditions that will hold for that variable as a class. So I'm going to give you later some examples of how we use this. But it says, you know, if we have a universe that X can belong to, phi will restrict that universe to a certain set of conditions. Okay, so kappa fun, less formally, because I'm not the formalist that Chad is, for example. Kappa fun is a class forming operator. It creates a class on the fly, usually in conditions where we have something we're trying to say that just isn't very common. You know, if we were going to use a reference to a certain class in multiple axioms, it had some meaning for us in the common sense world, we'd probably define it, we'd reify it, we'd give it a term name and say, all right, here's the definition. But if it's something weird that we're maybe only going to use once in one axiom, we want to create it on the fly and not clutter up the ontology. Let me return to variable arity relations. What are these things? What do they look like? Well, a common one that's used is partition, which says that a given class is partitioned into a set of subclasses that are an exhaustive decomposition of that parent class. And it's a variable arity relation because we can have multiple subclasses for every class that form a partition. So we give some type information. We say that the first thing must be a class. We also say the second thing must be a class. And we interpret this as holding for all of the subsequent possible relations in this variable arity relation. So here are two examples with different arity. Animal is decomposed into vertebrate and invertebrate, and organism is decomposed into animal, plant, fungus, and microorganism. All right, so it's just some basic biology, biological taxonomy. But how do we interpret this? So in THF, we have the type I to I to I to O. So O is, for those of you not familiar with THF already, it is the type of Boolean, but essentially the type of formulas. And I is everything else. I think this is Church's simple type theory, if I'm not mistaken. Right? And this notation, which I find rather funny, just means that we have three arguments for a predicate. As predicate forms a statement in this case. Right? If we were to just translate it this way into THF, we'd have just decided that there can only be three arguments. There's no notion inherently of a variable arity predicate in THF. And we could put a hack in there. We could create another version of partition that's I to I to I to I to I to O. I think it's one too many I's there. Sorry about that. So we do that actually in the first order interpretation, and we did that. I did that with Christoph years ago. It's a reasonable hack. It actually works. The problem is then we lose the connection between partition 3 and partition 4 and partition 5. They're distinct symbols, right? And there's no necessary mapping or connection between them. We'd like to get that connection back. And so there's a way to do this, fortunately, with sets. So we do is we treat, or I really should say Chad came up with this idea to treat the arguments themselves as a set. And so we create that set on the fly and just say that we have a predicate symbol that applies to this entire set. So instead of partition, animal into vertebrate and invertebrate, we have partition applying essentially to the creation of a list, and this list is forming a set. So we also then say that the return type, or the value of partition, is itself a funny sort of set. It's either singleton 0 or singleton 1 corresponding to true and false. And then we have a relation DP, which could be an abbreviation for Boolean to proposition, maps a set to a proposition when you need a proposition, or vice versa. So similarly, for this longer statements of 4 subclasses, again, we just turn it all into a list. So why do we want to do this again? Why not stick with the original THF translation that Christoph did? Well, Chad has this really cool proof called Megalodon that he's really into, and it's very powerful. And he also has a really detailed axiomatization of higher order set theory. So the idea is that we can simply do a better job figuring out whether the foundational stuff in SUMO is really 100% correct. We'd like to not keep going from year to year, hoping and thinking that it's mostly good and mostly okay empirically. We'd rather like to know that the basic ontological machinery of SUMO is really known to be correct. And so the idea is that with this very strict set theory axiomatization and the power of an interactive theorem prover and Chad's brain, that working all together, we can have a lot more confidence in this theory. Along with that, I think there's the potential that once we've done that, we may also be able to back off from some of this strictness and simplify, especially in terms of getting higher performance, because I'm actually not going to show you any of the automatically generated axioms that are the translation of SUMO into this higher order set theory application, because they're really big and they're really ugly, and I actually can't understand most of them directly. We'll have evidence by the correctness of the transformation and the correctness of the proofs in Megalodon, but inspecting these axioms is pretty tough. So that's one of our open issues of how we deal with that. So a little more formally, SUMO terms and the arguments to them become spines, list of terms that are translated then into sets, terms of type I. The propositions themselves are propositions, they're type terms of type O, and sometimes we need to coerce between I and O. There's an additional interesting thing about SUMO's classes. You know, I'm not a set theory guy, and so when I was starting to create SUMO, I knew we needed something about sets, and we need classes, and we need the notion of the class of all things, and we needed the class of abstract things, and these are a little risky. And so Chad came up with this idea of why don't we separate some of these potentially problematic things out to see if we can have a stronger guarantee of the correctness of the rest of the SUMO theory. How can we limit our universe of discourse to stuff that's far less likely to get into some sort of Russellian mess? And so we have class, setter class, the parent of class and set, abstract, which includes things like formulas and propositions, and entity, the class of all things. And we thought, let's add these essentially into the language and take them out of the ontology. I've had a bit of a philosophy that I don't like languages that put the ontology in the language. I wanted to just have everything pure and define it all. And maybe that was a little too risky. We'll find out. Maybe we can add these things back in once we prove that everything else is correct. So the interpretations of these 4 things are that they're not subsets of our universe of discourse, but rather we're calling them metaclasses. And the sort of the most important class then comes SUMO's class, which is interpreted as the power set of you, the power set of our universe of discourse. All right, so here's a very simple example of a proof. It's a proof sketch. I'm not going to show you code for it. It's all online, actually, as part of our GitHub repository. Chad and I are putting all this stuff. So if you really want to go into it, it is there. It does actually exist. But for now, I'll just give you a sketch. So this was actually a very simple little problem that we put into the TPTP. It's just first order, but it gives you a little illustration of what we do. So let's take an animal that, let's see, a rule that says an animal that has no part that is of itself, that is a spinal column, is not a vertebrate. Let Sluggy, this fellow here, be an animal that has no part of itself that is a spinal column. And we want to ask, is Sluggy an invertebrate? Well, we already know in SUMO, that has some background knowledge, that animal is partitioned into two subclasses, vertebrate and invertebrate. And so the sketch of the proof, which we can show you in great detail if you want to do it offline, is Sluggy first is not a vertebrate by 1 and 2, right? So he has no part that is a spinal column. And if he has no part that is a spinal column, then he is not a vertebrate. And so he's either a vertebrate or an invertebrate, which we know because we have this partition of classes. Therefore, Sluggy is an invertebrate. And it does this with sets. So that was pretty cool. Let me just skip that. Here's just another example of doing things with lists. So we've had a list function in SUMO for a long time that we've never really been able to use, but it's necessary to define a lot of stuff about variability predicates. We want to be able to pick elements out of a list, for example, and say that they're of a certain type. And so here's just some of the basic machinery. So let's see. So if we have nothing is in the empty list, is what this first one says. And then this is a sort of just recursive definition that if something is in a list with a head and a rest, it's either in the head or the rest. And let's say we want to make this query. Must every organism that is not an animal and not a microorganism be either a plant or a fungus, is what this works out to say. And we've got this additional information that the organism class is partitioned into 4 subclasses that we've already seen. And we have this that says every partition is an exhaustive partition and a disjoint decomposition, right? So if something in a set of classes, one class is partitioned into several others, then that set of classes is exhaustive. There's no other possibility of being a member of another class. If it's a member of the superclass, it must be a member of one of those subclasses, and also that they're disjoint. It can't be members of more than one of those subclasses. Here's the formal definition in SUMO of exhaustive decomposition. So if something is an instance of this parent class, then it must be in the list of things that are in the row, that are in the rest of the list of the subclasses. Right, so here's a proof of this test where we're going to see this: must every organism that is not an animal and not a microorganism be a plant or fungus? And so we have this proof sketch. Maybe I won't take the time to read through it. That's probably pretty obvious. And it's also, in some sense, maybe this may not be terribly exciting at first because this is something we've been doing in first order trivially for a long time. The advance is that now we're doing this with set theory, and with the idea that we can make sure it's more correct when we combine it with everything else. So this is just a first step. This is fairly early work. What's more interesting is dealing with things like kappa, the class forming operator. So let's say in some axiom, we already say that variable V is an atom. It's an instance of class atom. And we want to form this class here that is the class of all electrons that belong to that atom. So more formally, if X is our universal discourse, X is in both the class object and the class entity. These are both classes already in SUMO. We won't have to do this bool to prop conversion, right? To convert this relation here into a set. So it says that part is true of between X and V. So X is the electron that's part of V, the atom, and X is within the set of electrons. So here's a simple model of the atom. And let's say we want to do a query and prove for every atom V and every electron E that's part of V, E is a member of the class of all electrons of D. So it's just sort of recapitulating on an instance what we know to be true about Capricorn. And we can do this now. So a little bit of higher order stuff that we actually couldn't even do in Christoph Benzmüller's original THF formalization. So we've taken a big step to create some infrastructure, and then we've taken a baby step at proving something we couldn't prove before. So maybe I'll even be able to end a little early and catch us up somewhat on time. The conclusions here, the translations of each of these queries is provable using properties of sets. The translated axioms and resulting proofs are pretty horrific. I think we can do better. Hopefully we'll get over this first hump, proving things are correct. And so my hope is, yeah, we can validate the theories, but then simplify the code. Maybe. It's early work, I don't know. And in the future, in addition to the simplification, we're also trying to experiment with crypt key style possible worlds and accessibility relations. I have a lot more of that stuff that I could go into if anybody wants to talk offline about modals, and especially anybody that's an expert already in this sort of modal reasoning. I need to learn a lot of stuff. I've had a few people that have taught me little bits of this, and I'm doing lots of reasoning and lots of reading. But if you know more about modal logic and you're an expert in that, I would love to have some more tutorials and pointers. So thanks very much. I'll take some questions.
Tom, we have some, later.
Yeah, so a very interesting talk, and I'm excited to see this being embedded into set theory. My first question would be whether you really need a higher order set theory, because set theory is already pretty expressive. It's like just for translating high multiplarity relations and so on. I didn't quite see the need for predicates that map sets to sets. I mean, I understand you encode in a curried way multiple arguments, and that's fine when you continue with first order logic formalization of set theory. So, do you have the sense why? I mean, other than of course keeping some people involved that like higher order.
Yeah, there may be an element of that point, and I would need Chad here honestly to answer anything beyond that.
So maybe I can. So obviously, this is like these turtles. So of course, like you can do first order tasking rectangle, which gets you universes, and that's the way how to have set theories inside set theories inside set theories, and that's what like the semantics of things like Kok and Mizar is actually using to do these like bigger things that do not fit in your universe. But then Chad is convinced that a more elegant way how to do this is to do like the sort of higher order.
And then inside is there are no Tarski Grothendieck axioms, or you have both?
Yeah, he has that.
Okay, why it's more elegant? I guess that.
Well, because there is the high order automation, right? Like you get the lambdas and betas, etc. They're very more.
I would have another one.
But let's okay, Alexei.
So I just wonder, what about temporal reasoning? So you have shown one example, and it uses so-called time logic and maybe is explicit reference to time. Do you think that temporal logic would be appropriate also in this context?
Well, for each one of these different features in SUMO, yeah, there's a logic that already does it, or at least some interpretation or some idea of what that logic should cover, right? So there are temporal logics. The challenge that we have is trying to embed all of these things at once, right? I can't just use a temporal modal logic or a first order temporal modal logic, because I have epistemic operators and deontic operators and normative operators, right? And I want to be able to do all those things together. That Mary knows that Bill had an obligation to follow the law last Wednesday. Right? Things that we do effortlessly in natural language, and right now are sort of left out of our formalizations because these problems have been hard. Now, I don't know whether we're magically going to be able to come up to the answer with the answer to all this and have it perform in reasonable amounts of time so that it's actually practical to do queries with this stuff, but that's our lofty goal.
And maybe we should practice. Thanks a lot for
Thank you.
Thank you very much.